Hello everyone and welcome to my video on Introduction to Graph Theory using Python and NetworkX. This is the second class of a series, Review of Set Theory. My name is Innocent Okoloku. Objectives of the class today is to present a review of set theory, which is important for learning graph theory. The motivation: a good knowledge of set theory is essential for understanding some details of network and graph theory. Learning outcomes: at the end of this class, participants should be able to define some basic terminologies of set theory, describe and perform some basic set operations, describe and analyze the basic algebra of sets and duality, describe and analyze finite and infinite sets, describe and analyze classes of sets, describe and analyze power sets, describe and create set partitions, describe and analyze generalized set operations, define the principle of mathematical induction. Contents: definitions, set operations, union and intersection, set operations, complements and differences, fundamental products, algebra of sets, duality, finite sets, counting principle, inclusion and exclusion principle, classes of sets, power sets, set partitions, generalized set operations, principles of mathematical induction. So we'll go straight to definitions. A set is any well-defined collection of objects, usually denoted by the capital letters, for example A, B, X, etc. Objects, they are elements or members of a set and are usually denoted by small letters A, B, C, X, etc. Specification of sets: when we want to create sets, we just name the set using a variable in capital letter, and then we open these braces. Then we put the elements of a set, just like the way we learned it in Python. So what this means is we can use another description to create the set by writing the statement on the right hand side. We say X such that, now this stroke you are seeing here that is standing here is such that. X is such that X is an odd integer and X is less than 10. So the statement there is equivalent to the set we have here. You can be given the statement instead and asked to deduce the set out of it. This stroke here, which is such that, can also be represented by a colon. The colon or the stroke are used interchangeably. All of them mean the same thing, such that. We can also say B equal to X such that X is an even integer and X greater than 0. So can you guess what this is going to be? Even integers. We will start from 2 and then we'll go to 4, 6, 8, all the way to infinity. X greater than 0 means that X is any value that is bigger than 0 up to infinity. A set remains the same if its elements are repeated or rearranged. So a set is not ordered. It's not like a list, just like the way we learned it in Python. So let E equal to X such that X squared minus 3X plus 2 equal to 0. That's the set. So to determine the elements of E, we just have to take the number 0, 1, 2 all the way. We just substitute into this equation. We solve this function and get a value. The values will be 1, 2, either this F equal to 1, 2 or G equal to 1, 2, 2, 1, etc. Now a set is unordered. 1, 2 is equivalent to 1, 2, 2, 1, and it's also equivalent to what you have on this side. All of them are the same. Remember when we were learning about the set data type in Python, if you define a set in a certain way, Python, if you print it out, Python has probably rearranged it in another way because the order doesn't matter. And remember, items are not repeatable in sets. So no matter how many times you put 2 or 1, by the time you print it out, only 1 2 and only 1 1 will remain. So you see that E is equivalent to F and is equivalent to G. Then we'll talk about set membership. We are going to use these mathematical notations from now on. Please try to get used to them. So we say small a is in S, implies that small a is a member of set S. So you see this thing that looks like E here. In mathematics, it is inside. Just like in Python, when we want to check whether something is in a list, and then we say if X in the list. So this is the in. And this arrow you see pointing to the right means implies. Okay. We can also say A, B in S implies that A and B are members of set S. We can also say E, F not in S. Whenever you see this symbol that looks like E stroked out like this, then it's not in. It's not a member of a set. That implies that E and F are not members of set S. Let's go straight to see an example in Python to demonstrate basic set definitions and membership. So we call this program set 0.py. So let's begin with set specification. We say A equal to 13579. This is the normal definition, which we have seen before when we were learning about data types. We can also say AA equal to I for I in range 10 if I modulus 2 not equal to 0. So remember, we defined this set before in the previous page using two methods. This is the second method. What you see here is what we call set comprehension in Python. So we say the members of AA will be any I for I in the range 10, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if and only if I modulus 2 is not equal to 0. Certainly this will give you the odd numbers. So let's say we start from 0 and then we say 0 modulus 2, that is 0. So we won't have 0 as a member of a set. Then we'll go to 1. 1 modulus 2 is 1, the one you see here. Then we'll go to 2. 2 modulus 2 is equal to 0 because there is no remainder. Remember, the modulus is if we use 2 to divide I, are we going to get a remainder? If we don't have a remainder, then it's 0. If we have a remainder, it's likely going to be 1. So we'll go to 3. 3 modulus 2, remainder 1. And then we'll put the 3 here. And then we'll go to 4. It's going to be 0. You can't see 4 here. We'll go to 5. Modulus will be 1. And then we'll put 5 here. So on and so forth. Now, the reason why it stops at 9 is because our I is just in the range of 10. So we can print it. If you print A equal to A, what you get is 13579 like you see here. And if you print AA, what you will still get is 13579. So suppose you wanted to print out even numbers. So you know that for even numbers, the modulus will certainly be 0. It's the same method, just change the modulus to 0. So if you print it, you see 2, 4, 6, 8. Like I told you, Python is going to rearrange it because set items are unordered. So it can put the 8 first, put the 2 after, the 4 and the 6. It doesn't matter. How things are arranged in a set doesn't matter. It's the elements that matter. So we saw the quadratic equation before that we used to create the set E. If you want to do that in Python, it is like this. The set E equal to I for I in range 1, 10, or just say range 10. If I square minus 3I plus 2 equal to 0. See, what you see, this I here is a variable. It could have been x. If we had used x, it would have been, if x starts at 2, that is x squared minus 3x plus 2 equal to 0. So when you print it, what you get is 1, 2. And that's the set we saw previously. Now we talk about set membership. Let's say x equal to 8. We want to know whether 8 is a member of any of the sets here. So we say, if x in A print true, else print false. That's one method we can use to do it, the simple one which we know of. We can also use Python lambda. Let's move to a little bit of advanced Python at the moment. And we can say f equal to lambda k, true, if k not in E, else false. So what it is saying is, if a value k is not in E, print true, otherwise print false. It's the same thing we are doing here. So we call the lambda by just putting the value, any value. It could have been 8, it could have been 10. E only contains 1 and 2. If we had said print true if k in E, else print false, what would have printed out would have been false. So we'll go straight to Visual Studio Code and run this program and see how it runs. So here we are in the set0.py in Visual Studio Code. Because there are a lot of print statements here, it's going to be difficult for us to understand. So I'm going to comment out the remaining of the print statements and leave only one so we can see exactly how the program is flowing. We'll leave a comment here and start another one here and end it here. So we open AREPL because, as usual, this program doesn't require you to enter an input. So let's change something. Okay, our first printout, which is this definition, normal definition, gives us this A equal to what we have here. Now let's see the second definition, what it prints out, AA. It still gives you the same value. Let's look at B. 82468, correct. Let's look at E. 1, 2. So let's look at set membership. We check the first statement. If 8 is in A, print true, otherwise print false. Certainly 8 is not in A, you can see it here, and so that's why I printed false. And finally we can look at the last print. If 10 is not in E, print true, otherwise print false. Of course 10 is not in E, that's why I printed true. We are back in our presentation. Let's look at some definitions. Subsets. Set A is a subset of B implies that the set A is contained in B. That is, all the items in A are contained inside B. Now look at the subset notation here. You see this is proper subset. We will define it later. And this one equal to here means subset. So the equal to here is what makes it a subset. What this means is that you can find all the elements of A inside set B. At the same time, the equal to here means that it is possible that the elements of A and the elements of B are exactly the same. So any set is a subset of itself, but is not a proper subset of itself. So when we say B not a subset of A, what does that imply? If we use this symbol, it's only saying that some or all the items in B are not in A. That's what we mean by not a subset. When you strike it out, it means not a subset. Okay. So some other things we need to know is, if A is a subset of B and at the same time B is a subset of A, it implies that A and B are equal. We talk about proper subsets. If A is a subset of B and A is not equal to B at any time, then it implies that A is a proper subset of B. This is what I was trying to describe before. Meaning that you can find every element of A in B, but the elements of A and B are not equal. The elements of A are less than B, so you can say that A is a proper subset of B. If A is a proper subset of B and B is a proper subset of C, that means that A is also a proper subset of C. We will see examples of all this as we are going on, so don't worry if you are not grasping the definitions perfectly at the moment. Then we have special symbols, mathematical symbols. We have something called N. This capital N is the set of natural numbers. See, we are going to be working with these ideas as we progress, so it's good for you to know them now if you've forgotten them from elementary mathematics. So the set of natural or positive numbers are 0, 1, 2, 3. We'll call them the natural numbers, whole numbers. Then we also have Z, which is the set of integers. The difference between the set of natural numbers and integers is Z starts from minus infinity to plus infinity. N starts from 0 to plus infinity. And then we have Q, the set of rational numbers. Rational numbers are numbers that when you divide them, the decimal point stops at somewhere. It doesn't go to infinity. For instance, pi, which is 22/7, is not a rational number. Because when you divide 22/7, the decimals trail to infinity. Your calculator is only trying to approximate it for you. So the set of rational numbers also contain integers, because for instance 2 is 4 divided by 2. So you use 2 to divide 4 and you just get 2.0. That is rational. And the rational numbers begin from minus infinity to plus infinity. And then we have the set of real numbers. The set of real numbers contains both rational numbers, integers, natural numbers, everything from minus infinity to plus infinity. And then we have the set of complex numbers. The set of complex numbers contain also the imaginary part. So any number you write is actually a subset of complex numbers. For instance, 2, for example, is the same thing as 2 plus 0 imaginary part. So the set of complex numbers contains the set of real numbers, the set of rational numbers, the set of integers, and the set of natural numbers. In fact, if C contains arrow, it means that C contains everything. As you can see from this analogy, N is a subset of Z, and Z is a subset of Q, and Q is a subset of R, and R is a subset of C. So complex numbers were invented to solve a lot of problems in mathematics, and they are very useful. For instance, if I ask you to find the square root of -2, it will be difficult for you to find it ordinarily unless you use the ideas from complex numbers. So we are still looking at definitions. We talk about the universal set, which is indicated by this U. When you say a universal set, the term is relative. It is all sets under investigation in a particular application of set theory. So let's say we are investigating the set of mammals. So the universal set is mammal. Every kind of mammal is in the set. So let's say we are investigating the set of flowers. So the universal set will be flowers. So you define the universal set depending on what kind of problem that you want to solve. There is also the concept of the null set, which is the empty set. So we just create that by creating this empty set here that you have here. There is nothing inside it. For example, we can create a set and say x is equal to x such that x is in the set of natural numbers, x is greater than 1 and x squared is equal to 1. This kind of arrangement does not exist. We will use a program to prove it later. So let me explain it a little bit clearly here. So we say we want to create a set S, and the S is going to be a natural number which is greater than 1, and that number, if you square it, the value must be 1. So since n is greater than 1, we must be starting at 2. If you square 2, are you going to get 1? No. If you square 3, are you going to get 1? No. Which means that the set is going to be empty. That's an example of a null set. Later on, we see a Python program that actually tries to create this set, and you discover that it is a null set that comes out. So the null set is regarded as a subset of every other set, meaning that phi, which is a null set, is a subset of A, which is any other set, and A is a subset of the universal kind of set. So if we are considering the set of flowers, for instance, there is a null flower which does not exist. We don't know about it now. It may be discovered donkey's years from now, we don't know, but it doesn't exist. But we know that this non-existent set is a member of every other kind of flower. So maybe we talk about the set of hibiscus flowers, which is a subset of flowers. So we have disjoint sets. This is two sets that have no common elements, two or more sets that have no common elements. So if we create three sets and say A equal to 1, 3, 5, 7, B equal to 2, 4, 6, and C equal to 2, 6, 7, 8. Now if you look at these two sets, A and B, do they have any common elements? It's like A contains only odd numbers and B contains only even numbers. So A and B are disjoint. They don't have anything in common. What about B and C? B and C have 2 in common and they have 6 in common, so they are not disjoint. What about A and C? Now, to show this kind of relationships, Venn diagrams are usually used. So let's say we add another set and call it D equal to 1, 3. First of all, we want to look at the proper subset. D is a proper subset of A. Why? Because every item in D is inside A, but there are some items in A that are not inside D. Therefore, A and D can never be equal. In that case, we can say D is a proper subset of A. See, the equal to that is supposed to be below it is not there. Okay, so we'll cancel this out. And U is the universal set for this particular problem. Secondly, we see that A and B are disjoint. So you draw the set A and you draw the set B and they have no contact. For the first one, because D is all the items of D are inside A, that's why the D is inside the A here. So what about when they are not disjointed? Meaning that they intersect. Set intersection. So this is B, 2, 4, 6, and this is C, 2, 6, 7, 8. They have 2 items that are common to each other, and those items are 2 and 6. So it is 2 and 6 that brought them together. Union. The day a young man and a young lady get together and get married, if the young man has a family, a mom or a dad, the mom and dad becomes the mother-in-law and the father-in-law of the young lady. And if the young lady had parents, the parents become the parents-in-law of the young man. That's the idea of what union is about. So the young man and the young woman brought the families together. They are now intersecting. So let's go straight to see an example of this code in Python. We'll call this set 1 to demonstrate null set, subset, intersection, and disjoint sets. First of all, we'll create a null set. What you see here, this E, is just the previous one, the set S that we are trying to create. So we say E equal to I for I in range 110 if I square equal to 1 and I greater than 0. Nothing like this exists. Like in the analysis I was doing before, we start from 2 and the square of 2 and any number bigger than 2 can never be 1. So this condition here can never be satisfied. And if you run it, you will see that it gives you an empty set. So let's create some test sets from the examples we saw previously. We say A equal to 1357, and then we say B equal to 246, and we say C is equal to 2678, D equal to 13. Is D a subset of A? Can we do that with Python? We say F equal to lambda K. We are using Python lambdas now. True if K dot is subset A, else false. So any K variable that we are going to give this function below, we test it. If K is a subset of A, then print true, otherwise print false. So we can now call this lambda function by using fd. So we want to say if D is a subset of A, print true, otherwise print false. Definitely it's going to print true because D is a subset of A. In fact, it's not just a subset, it is a proper subset of A. Are A and B disjointed? We can see already that they are disjointed. So we say F equal to lambda K, true if K dot is disjoint A. Take note, you are using KK here as a variable when you are using lambda. So we call it and we put B here. And this is going to print true because A and B are actually disjointed. There is no union. Again, we can say, do B and C intersect? We can already see that both of them intersect. You will use lambdas again. F equal to lambda K, false if is disjoint C, else true. Print false if they are disjointed. Otherwise, print true if they are not disjointed. That is, they are intersecting. Of course, they are intersecting, so it is going to print true. So we'll go to Visual Studio Code and run this program and see what happens. So here we are in Visual Studio Code and we are looking at set 1. Okay. Now there's a lot of printing going on here, but it's not too much. I'm not going to use doc screen comments. I'm going to use normal comments to comment this out. Open ARAPL and try to make an update. So let's say we update this. Okay. Whenever Python is printing something like this, it doesn't actually print value, it just says set empty. You know it's a null set. That is equivalent to printing E equal to open parenthesis. So let's look at the second output. We want to test if D is a subset of A. We uncomment this. Of course, D is a subset of A. In fact, it's a proper subset. Now we want to test if A and B are disjointed. No union. That is true. A and B are disjointed, as we can see, or as we have analyzed before. Then we want to test if B and C intersect. That is true. B and C actually intersect. Now we are printing true, true, true because of the way we wrote the lambda functions. If you write it the other way around, it can print false. Now let's look at set operations. We begin with union and intersection. Union. The symbol is A, and this thing that looks like U is A union B. It is a set of elements X such that X is in A or X is in B. And is denoted by using something like this. A union B. This is the universal set. So A union B is either X is in A or X is in B. In fact, the elements that are together, all of them together form the union of a set. So you see this shaded region, everything that is shaded here is a part of the union. Then we'll talk about intersection. It's the set X such that X is in A and X is in B. only the elements that are in both of them form the intersection. So the intersection here is just this part of the diagram. Okay, that's A intersection B. For example, let U be the set of students in a class where M is the set of male students, F is the set of female students. So we say the union is M union F, and you can guess what that will be, the total class of all sets of male and female students coming together. What about the intersection? Can there be an intersection between male and female? Maybe it's possible that some of the guys in there are biological situations where somebody has both genders, so maybe there could be an intersection, but normally there should be no intersection, and this M intersection F should be null. Example 2. Let A equal to 1, 3, 5, 7. We are still using our previous sets. And then we have B equal to 2, 4, 6 and C equal to 2, 6, 7, 8. A union B is 1, 2, 3, 4, 5, 6, 7. Take note, the union brings everything together. A union C is 1, 2, 3, 5, 6, 7, 8. What about B union C? Can you guess? So the elements are going to be what? Elements cannot be repeated. So we'll have 2, and we'll have 4, and we'll have 6. So since 2 and 6 are already here, the only thing we need to pick out will be 7 and 8, is it not? 7, 8. Alright. What about A intersection B? Of course it is null because there is no relationship. We've seen that before. What about A intersection C? 7. What about B intersection C? Now let's look at some properties. If we have a set D and it is intersecting E, whatever this intersection is, it is a subset of D. It is also a subset of E. Let's use B intersection C to do the analysis. If B and C intersect, these are the elements. It means that you can find these elements either in B and you can find these elements either in C. So that's why we say we can find this element here either in D or we can find the same element inside E. So if we say D and F intersect, what do we say? We are saying that this D and F intersection can be inside D and it can also be inside F. And if E and F intersect, any arbitrary sets E and F, we can find the elements of this intersection in E and we can also find it in F. Second property, D is a subset of D union E. D must be inside the union of a set that it makes. So let's take this analogy, this example. A union B. Union means that you can find all the elements of A inside here and you can find all the elements of B inside here, which means that A is now a subset of the union. In the same way, you can guess that E is a subset of the union also, because it was the union of D and E that created the bigger set. Union creates a bigger set. Intersection creates a smaller set. So if we say F is a subset of what? We are trying to say, just first of all, F is a subset of itself, and F is a subset of itself and the union of any other set whatsoever, called the set X, whatever I want to call it. Therefore, if D intersection E is a subset of D, it also implies that D, from this second property, is a subset of the union. Intersection is smaller. The set, whatever set D or E, is bigger than the intersection. At the same time, whatever set D or E is smaller than the union. So when we say D intersection F, what is it a subset of? It is a subset of either D or F, and whether D or F, it is a subset of D union F. So can you also make some conclusion from this side? Think about that yourself from the example I've given. The following are equivalent. Now again, you see this notation. Anytime you see FF, just know that it is following. The following are equivalent. D is a subset of E. D union E equal to E. If the union is equal to E, it means that D intersection E is what? Let's look at it this way. This is E. If D union E equal to E, it means that the whole of D is inside E. So where do D and E intersect? Certainly they intersect in D. Now let's go and see a Python program that displays whatever we have been talking about. The first thing we are going to do is create all those sets that we just saw now. All the sets A, B, C and D, they are the same elements. This is to demonstrate union, intersection and disjointed sets. So we start with union. Print A U B equal to A dot union B. See, I'm just using print to make our coding shorter. You could have declared a variable and say maybe C equal to A union B, but no need to do that. Let's just print it out. So it's going to print the union 1, 2, 3, 4, 5, 6, 7. All the elements coming together. We can also say print A union C, and it's A dot union C. There is another way to do it, but this is one way to do it. So A union C will just bring the elements of A and C and put them together in one set. Now let's look for intersection. B intersection C. We just say B dot intersection C, and that will give us 2, 6. And we can say A dot intersection B. See, A and B don't intersect because they don't have any common elements, and that will give us the null set. And we can also say A intersection D. A intersection D is what? Because D is totally contained in A, is a proper subset of A, the intersection is going to be D. That's the elements are 1, 3. So we'll go to Visual Studio Code and run this program and see what we get. So here we are in Visual Studio Code. We will comment the other print statement so that things can be easy. Update this code. Right, so we have our A union B, which is correctly printed out here. A union C, correctly printed out there. B intersection C, 2, 6. A intersection B, null. A intersection D, exactly all the elements of D. So let's talk about some more set operations, complements and differences. The complement of a set is usually denoted by this A to the power of C, which means that the set of all X such that X is in U and X is not in A, which is the negation of a set. So if a set contains certain elements, the complement of that set is every other element that is not in that set. It's like negation or opposite. Now, this notation you see here, A to the power of C, in some books it will be written as A to this prime or A bar. All of them means the same thing, so don't get confused. Now there is also something called the relative complement of a set, which is difference. The relative complement of set B with respect to set A is the difference of A and B, and it's usually written like this. That is, if you have a set A and you have a set B, if they have certain items in common, if you remove all the items of B from A, what do you have? it is the set of all x such that x is in A and x is not in B. So we'll remove every item that was in B from A, and that's what we get, the relative complement, which is also the difference. We see examples as we progress. So another way to write it is we say A complement B equal to A minus B, or we say this A tilde B. All of them are the same in the books. There is also something called symmetric difference. The symmetric difference of A and B is the set of elements in A or in B, but not in both of them. The set of elements in A or in B, but not in both of them. So it is usually denoted by using this symbol. A symmetric difference B is A union B minus A intersection B. Just remove the intersections, which is also equivalent to the difference of A and B union the difference of B and A. So the first one is take all the elements of B from A, then take all the elements of A from B and put them together. You get a symmetric difference. We see examples. So the first one you see here is, this is set A, this one is set A, everything here. Now everything outside set A is the complement. Everything on this side that is not, the items are not inside A, is the complement of A. The difference between A and B is when you take all the items of B from A, what you get is everything on this side. Nothing from here and nothing from here. That is A bar B. In the same way on this side, what you have here is B bar A. In this part, the symmetric difference is the set of elements in A or in B, but not in both. So what we have here now is we take this A bar B and we unite it with this B bar A, is what we have here. So everything you see on this side union everything you see on this side is what this is. Okay, let's look at an example. Let U be this universal set. So our universal set is the set of natural numbers 1, 2, 3, 4 up to infinity. Also, we define the following sets: A equal to 1, 2, 3, 4, B equal to 3, 4, 5, 6, 7, C equal to 3, 2, 3, 8, 9, and E equal to 2, 4, 6. Then A complement is, since the universal set is 1 to 3, we are going to look at items from 1 to 3 up to infinity that are not in A, and that does what? Begins at 5, 5, 6, 7. All the numbers to infinity are the complements of A. What about the complements of B? Since you are dealing with natural numbers, 3, 4, 5, 6, 7. So we have B complement is starting from every item that is not in B. So we have 1, 2, 8, all the way to infinity. What about the complement of E? Can you guess that? So if we say A minus B, look at the items that A and B have. What do they have in common? 4 in common, 3 in common. So 3 and 4 are in B. We are now going to remove the 3 and 4 from A. And so the only thing we have is 1 and 2. What about A minus C? It's the same thing we do. The common items between A and C are 2 and 3. So we'll remove the 2 and 3 and then we have 1 and 4. So what about B complement C? What about A minus E and B minus A, C minus A, C minus B, E minus A? I leave this to you as exercises. The more you practice them, the more you will understand what's going on here. We've seen complements, we've seen difference. We're now talking about the symmetric difference of A and B. Like we saw in the earlier analysis, the symmetric difference is for this part, this first part. What we did here was remove every item in B from A, and then we got this 1, 2. And in the second part, remove every element inside A from B. So if we did this B minus A, 3 and 4. So if we remove 3 and 4 from here, we have 5, 6, 7. So the union of this and this gives us 1, 2, and the second part is 5, 6, 7. What about A? Symmetric difference C. This is the value that we get. Can you try to figure out how this value came about by using the example we just did now? And what about B, C, and A? Try your hands on all of these exercises and you will get stronger. Example 3, to demonstrate set complements and differences. So we create the test set. Our universal set has to be limited. We know it goes to infinity in what we wrote, but we are dealing with computers. It's not practical to be dealing with infinity. You spend a lot of time running the program. So let us limit our universal set to 1 to 10. So we say A, like we described before, B, like we described before, C, and E. Test complement. Print AC equal to U dot difference A. See that we are using the universal set now. So A complement is every item in the universal set that is not in A. So we use difference. Of course, there is another method to do it, and in the second method we just use the minus sign. So if we say B complement, it is B subtracted from the universal set. Talk about difference. The difference between set A and B is just A minus B. So we say print A minus B equal to A minus B, which will give us 1, 2, as we did before. Another method is to call the function or the method A dot difference C or whatever set. So A minus C can also be A dot difference C, and that gives us 1, 4. Symmetric difference A XOR. It's not really exclusive OR, but I just use this XOR to indicate that symbol because it is only exclusive OR that looks very close to that symbol. So we say A dot symmetric difference B, and that gives us 1, 2, 5, 6, 7. Or we can use a symbol, this caret symbol, the symmetric difference of A and C, A caret C, and that gives us 1, 4, 8, 9. So we'll go to Visual Studio Code and see how the program runs. Here we are in Visual Studio Code. It is set3.py. We will comment out a lot of the other print statements to make it easy for us. So from the universal set, A complement is all the items that are not in A from 5 to 10. We can see that there. B complement is all the items that are not in B. Difference between A and B, 1, 2. A between A and C, 1, 4. Symmetric difference between A and B, 1, 2, 5, 6, 7. Symmetric difference between A and C, 1, 4. Let's look at set operations. We begin with fundamental products. A fundamental product of n sets A1, A2 to AN is a set of the form A1 asterisk intersection A2 asterisk intersection all the way intersection AN asterisk, where A asterisk indicates A or the complement of A. Notes: there are m equal to 2 raised to power n of such fundamental products, depending on how many sets you have. Any two such fundamental products are disjoint. U is the union of all fundamental products. Let's take an example. The following lists the M fundamental products of sets A, B, and C. P1 equal to A intersection B intersection C. P2 equal to A intersection B intersection C complement. P3 equal to A intersection B complement intersection C. P4 A B complement C complement. P5 P6 P7 P8. So it does depend on the number of sets you are dealing with. So we have 3 sets, that's why it is raised to 2 to the power of 3, and that gives us 8. Now an easy way to understand how to create this is by writing it out using binary numbers. So if you start with 0, 0, 0, 0, 0, 1. The next one will be 0, 1, 0. The next one will be 0, 1, 1. The next one will be 1, 0, 0. We are counting from 0 to 7 using binary numbers. So we have 1, 0, 1, 1, 1, 0, and finally 1, 1, 1. So if you follow this binary counting, you can generate the fundamental products of any number of sets. You just have to patiently do it straightforward and be careful that you are not counting wrongly. So when we put the 3 sets together, A, B, and C, this is what we have. So in this diagram, you discover that the first fundamental product P1 is the intersection of all of the sets, all of them together. The second fundamental product, which is P2, is the intersection of A and B, so on and so forth. And you discover that the last 3 are the items that you have on the outside. So you can see how you can use fundamental products to solve complement relationships and the other things we were describing before. If I want you to give me the XOR of A and B and C, I am saying the union of everything that is on the outside alone. So what you should do is see how you can actually use these fundamental products to provide solutions to the problems we previously described very quickly, just by doing this thing, which is similarly easy to do here. If you can build this, you can be able to solve the problems very quickly without a lot of mathematical rigor. Now let's look at the topic of algebra of sets. We're looking at duality. The following laws are followed in the algebra of sets. So first of all, we'll look at the law, then we'll look at the union law, and we'll look at the intersection law. We'll talk about the idempotent laws, or the law of idempotency. A union A is A. A intersection A is also A. The law of association. A union B in bracket everything union C is the same thing as A union in bracket everything B union C. A intersection B everything intersection C is the same thing as A intersection B intersection C. Commutative laws. A union B is the same thing as B union A. It doesn't matter which of them comes first. It is union, is union. A intersection B is B intersection A is the same thing. Distributive laws. A union B intersection C, where the B intersection C is in bracket, is equal to A union B intersection A union C. So it's like we are expanding. A intersection B union C is the same thing as A intersection B union A intersection C. You can prove these things by using small sets. Identity laws. A union phi is A, and A union, the universal set, is the universal set. A is already inside the universal set. So the union is the same thing as the universal set. A union phi is A because phi is already inside A. Phi is the empty set, the null set, doesn't exist. So we assume that the set that does not exist is inside any set. So it's the same thing as A. A intersection phi is phi because the empty set is inside A, so the intersection is nothing. I mean, if A intersects nothing, then it is nothing. Okay. So A intersection U is A. See, this is the intersection. So that's why this is phi, and that's why this is A. Involution laws. A complement, everything complement again is the same thing as A. It's negation, negation. It's like you are saying 1 over 2 and everything 1 over. It goes back to what it was before. Negation, negation. So you say minus minus A is the same thing as A. Becomes plus A. Complement laws. A union A complement is the universal set. So this is A and this is everything here is A complement. So we'll put all of them together again. What do we get? The universal set. The complement of the universal set is the null set. That is the set that does not exist. A intersection A complement is phi. So when we say A, what is A complement? A complement here is everything outside that does not contain A itself. So if everything outside does not contain A itself, then there is no intersection. The complement of the null set is actually the universal set. So these things are very easy. You can see them, analyze them, and bring them from your head without needing to look at the formula. Now we have the De Morgan's laws. A union B complement is A complement intersection B complement. You can prove this. A intersection C complement is A complement union B complement. So just take note of the De Morgan's laws. When you have a union and a complement, it changes to intersection and separate complements. And when you have an intersection and a complement, it changes to a union and separate complements. Prove it using two sets. Now we'll talk about the principle of duality. For an equation of set algebra, the dual E asterisk of E is obtained by replacing every occurrence of U, intersection, universal, and null with the opposite. Replace union with intersection. Replace intersection with union. Replace universal with null, and replace null with universal. So if I say if H equal to U intersection A union B intersection A, what will be the dual? The dual will now be phi union A intersection B union A. Every union has been changed to intersection, and every intersection has been changed to union, and every universal has been changed to null. Check it out. If you find any error here, maybe I'm not seeing well, drop in a comment. Let's look at finite sets counting principle. A set is finite if it is empty or it has exactly m in n elements, where n is a set of natural numbers. Otherwise it is infinite. We cannot count it. For example, the English alphabet and the days of the week or year, all of them are finite. Example 2. The set of positive even numbers and the unit interval are also finite. So we have a set K equal to 2, 4, 6, and we have a set which is a finite interval X such that 0 less or equal to X less or equal to 1. These are finite. The set of alphabets contain 26 items, is it not? and the days of the week contain 7 items. 7, 26. These are finite sets. A set is countable if it is finite, or if its elements can be arranged in a sequence. So in set theory, when we want to indicate how many elements are in a set, we use this either ns or absolute value of s. So this is the number of elements in set S. Then we can say the number of alphabets, n alphabets, is 26. And nd, sorry, this will now be d, days of the week. nd equal to 7. And the number of items in the null set is 0. Let A and B be finite disjoint sets. Finite and disjoint. Take note of this. There is no connection. If a set is disjoint, it means that the union of a set contains every element of A and every element of B. So we can say NQ, which is the same thing as NA union B, is equal to the number of the elements of A and the number of the elements of B. Only if they are disjoint. If they are not disjoint, we see that something needs to be removed from the addition in order to get the counting or the count of a set. Let A and B be two finite sets, not necessarily disjoint. Then the number of the difference between A and B is the number of A minus the number of the intersection. Still on counting principle. We'll look at an example. A computer science class has 46 students. Out of these 46, 15 of them are taking a mathematics class B. What is the number of students in class A which are not in class B? Of course, it's easy for you to just look at this with your eyes and know what the answer is supposed to be. But let's follow it using the ideas we just learned, so that when you see a more complicated problem which you cannot just solve with your eyes, you can also apply those principles and get a solution. So we say we want to separate the number in set B from the one of A. So that is NA minus NA intersection B. 46 minus 15, that gives us 31. Which is obvious, of course. Let A be a subset of a finite universal set U. Then the number of A complement is the number of the universal set minus the number of set A. Example. Suppose a universal class has 35 students, and out of that 35, 20 are full-time students following this. So we say n complement equal to nu minus na, which gives us 35 minus 20, 15, which is also obvious. Now let's look at the inclusion-exclusion principle. Suppose A and B are finite sets, not necessarily disjoint. They are not disjoint now, so they probably have an intersection somewhere. Then A union B and A intersection B are also finite. In this case, we say N A union B, which we previously described before for disjoint sets, will now be NA plus NB minus the intersection. It has to be removed. So suppose A, B, and C, we are extending it further now to 3 sets. The previous one we dealt with 2 sets. Then the number of A union B union C is the number of A plus the number of B plus the number of C minus the intersection of A and B minus the intersection of A and C minus the intersection of B and C plus the intersection of A intersection B intersection C. We see that in an example. Suppose a list A contains the 30 students in a mathematics class, and a list B contains the 35 students in an English class, and suppose there are 20 names on both sides. Find the number of students in A only in list A, B only in list B, C on list A or B or both, and D exactly on one list. Now this is a simpler problem which we will solve with the case for 2 issues, 2 sets. First solution. We are looking at, see, the first question is only in list A. Since we are dealing with two sets, we are going to remove the set B from set A, which is obvious. The number of A minus the number of A intersection B, which gives us 30 minus 20, and that is 10. The second one is also obvious, only in list B. So we are taking A from B equal to the number of B minus the number of intersection equal to 15. Question C, on list A or B or both. So we use the inclusion principle, inclusion exclusion principle that we just described, and that is A, number of A plus number of B minus number of A intersection B. So that's what, 30 plus 35 minus 20, and that gives us 45 students. For the part of D, exactly on one list, we are looking for the number of this, what we have here, symmetric difference. So that will be the number of A exclusion B and the number of B exclusion A. So these problems which we solved using diagrams before, you can actually solve them using the Venn diagrams that we described before, but we are now solving it algebraically. Sometimes you may get into a test or an interview where they say solve this thing without using Venn diagrams. You should be able to apply this inclusion exclusion principle to get a solution. So if we solve that, we get 10 plus 15 minus 0, and what we have is 25. So we take this solution, and then we see whether there is anything like this. The intersection of A exclusion B and B exclusion A, there is no intersection. It is far, it is 0, because when we solve this problem, we removed every B from A, and when we solve this problem, we removed every A from B. So there is no intersection, and that's why we have this 0. So the answer is 25. Classes of sets. So we can have classes or collection of sets, and we can also have subclasses or subcollections of sets. An example, given S set S equal to 1, 2, 3, 4, let A be the class of subsets of S which contain exactly 3 elements. Exactly, take note of this. Then A will be what? We pick out every combination of 3 elements in the set we have here. So we can start with 1, 2, 3. Then we say 1, 2, 4. What's remaining? And then we say 1, 3, 4. And then we say 2, 3, 4. This is the set. You can't have any other combination of 3 items from S. See, you cannot just create another set and say 2, 3, 1, 2, 3, 1, or 1, 3, 2. All of them are the same thing, because the arrangement of a set does not matter. So as long as there is 1, 2, and 3 here, you can't create any other set that contains 1, 2, 3. Let B be the class of subsets of S, each which contains 3 and any 2 other elements of S. So we are going to create this class of subsets that must contain 3 and any other 2 elements. 1, 2, 3 is a part of it. 1, 3, 4 is another part of it. And 2, 3, 4 is another part of it. So we have these three sets that satisfy the condition here. Again, let C be the class of subsets of S, each which contains 4 and any other element of S. Can you guess what that is already? Any other element means that there are going to be 2 elements, and each of those 2 elements of sets you are going to create must contain the number 4. So what is C? Think about it. Power set, denoted by PS, is the class of all subsets of a given S. The class of all subsets of S. If S is finite, so is PS. So we write it like this. NPS equal to 2 to the power of NS, where N is the number of items in S, the countability of S. So for this reason, PS is often denoted as 2 to the power of S. Is the same thing. Let's look at an example. Given S equal to 1 to 3, determine the power set. So power set implies how many sets can you actually create from the elements of a set. So we already know that 5 is a part of any set. So we have 1, we have 2, we have 3. Every item of a set must be a part of a power set. And then we start taking combinations. 1, 2, 1, 3, 2, 3, and finally the whole set itself, 1, 2, 3, is a part of it. So when you count it, you have 1, 2, 3, 4, 5, 6, 7, 8. So since the number of items here are 3, the number of items you must have in the power set must be 2 raised to the power of 3. So if the items were 4, you will have 16. So that gives you an idea of what you are supposed to create if somebody asks you to create a power set of a particular set. So we say n p is equal to 2 raised to the power 3, and that is it. So if I give you this set of 4 items and ask you to create a power set, how can you go about that? Exercise your brain on that. It will make you understand it better. Now let's look at set partitions. A partition of a set is a collection AI of non-empty sets such that each A in set S belongs to one of the AI. The sets AI are mutually disjoint. Take note of this. That is, if AI is not equal to AK in the partitions you are creating, then the intersection of AI and AK must be 5. There is no union. This is a rule. These are 2 rules that must guide the creation of set partitions. The subsets in a partition are called cells. So let's take an example. Given S equal to 1, 2, 3, 4, 5, 6, 7, 8, and if we try to create partitions out of this S, I will give a list of items here, and out of the items I'm giving, only one of them will be a real partition. The rest will not be partitions. This is to help us understand how to create partitions. So suppose I have a breakdown of the list of the original set like this, and then I have another breakdown like this, and then I have another breakdown like this. Which of them is actually a partition? Only number 3 is a partition. We will now know why is it that only number 3 is a partition. We go back to look at the 2 rules that we must follow. Each A in S belongs to AI. So every item here should belong here. We start counting. 1, 3, and 5. 1, 3, and 5 are here. 2 and 6. 2 and 6 are here. 4, 8, 9. 4, 4, 8, 9 are here. What about 7? 7 is not here, so this is not a partition. The second one is 1, 3, 5 are here. 1, 3, 5 are here. 2, 4, 6, 8 are here. 2, 4, 6, 8 are here. 7, 9 are here. 7, 9 are here. But 5 is repeating itself the second time. So they say the sets are mutually disjoint. There should be no union. So this one violates the rule. The only set that actually does not violate the rule of partition is this one. So this is what makes number 3 the only set partition that is correct there. So you should know how to partition sets. If I give you an example and say 1, 3, 4, 6, 7, 8, 9, create a partition, how would you go about it? Exercise yourself. Let's look at generalized set operations. Set, union, and intersection operations can be applied to sets of any dimension, whether finite or infinite, as follows. Consider a finite number of sets A1 to AM, then A1 union, A2 union, up to union AM. See, when you want to indicate unions of sets, you just say union. You can write everything out, and union again. So everything will be indicated by union. I equal to 1 to MAI. Their equivalent is the set of all X such that X is in A AI for some AI, whatever the AI from 1 to m. In the same way we describe the intersection. So get familiar with these symbols whenever you see them in a book. Then let this script A be any collection of sets, not necessarily finite. Then the union is A such that A is in the cryptic A. Any set A such that A is in the cryptic A, which implies that it is an X such that X is in AI for some AI in A. The intersection is similarly defined as X is in AI for all. Take note, for some. This symbol you see here means for all. For all. ALL. For all AI in A. Example. Consider the sets A1 equal to 1 to 3, the set of natural numbers, and A2 equal to 2, 3, 4. Sorry, we have been omitting the 0. It doesn't matter, okay? A2 equal to 2, 3, 4, and A3 equal to 3, 4, 5. AN equal to N, N plus 1, N plus 2, so on and so forth. Then the union and intersection are as follows. UAK for K in N is equal to N. So if we say A1 is 1, 2, 3 all the way down, then we have 3 and 4. See, 3 and 4 is already inside A1. A3 is already inside A1. And even AN is already inside A1. No matter what N you put here, it's still in the set of natural numbers. So the union is in the set of natural numbers. So intersection AK is equal to 5. Now from the way we've learned about intersections before, you might say A3 intersects A1 because of the common terms, and A2 also intersects A1. However, the way the generalized intersection is defined here, X must be in every set. So 1 is in A1 but is not in A2, is not in A3. So that is enough to violate the rule for intersection, and that's why the intersection is 5 for this one. Generalized De Morgan's laws. For some collections of set AI, we say the union of A such that A is in A, cryptic A complement is equal to the intersection of A complement such that A is in cryptic A. I want you to analyze this if you have the time. Also in the same way, this is union, changes to intersection this way. Remember our principles that were considered in the last few slides. Intersection changes to union. Before we go, we'll look at the principles of mathematical induction. We'll look at two principles. So we say PMI, principle of mathematical induction. 1. Let P be a proposition, that is a statement put forward, defined on the positive integers n, such that Pn is either true or false for each n in n. Suppose that P has the following two properties. P1 is true. Pk plus 1 is also true whenever Pk is true for k in the set of natural numbers. Then P is true for every positive integer n in n. This is obvious, you can see it from there, because we are counting from 1, 2, 3, 4. So it's true for every positive integer. That's proposition 1. Principle of mathematical induction 2. Let P be a proposition defined on the positive integers such that P1 is true, Pk is also true whenever Pj is true for all 1 less or equal to j less or equal to k. Then Pk is true for every positive integer n in n. Now, you are not required to prove this. You are just required to understand it a little bit, as much as you can, okay? So, we have come to the end of the class today, but before we go, we'll look at our homework and lab 2. First one is, in the course of this note, I've been leaving a lot of exercises undone by giving you an example. So, You can help yourself by going through the exercises in pages 12, 15, 18, 22, 23. Try your hands on them. Second question is a challenge question. We've seen an example for 2 sets. Now I'm extending it to 3 sets. And you can follow the same principles that we used before to solve the one of 2 sets to get the solution of this one. The populations of 3 communities are A equal to 68, B equal to 55, and community C equal to 70. Suppose a company D has 22 workers from all the communities. Company E has 10 workers from A and B. Company F has 12 workers from B and C. And company G has 15 workers from A and C. Find the population of people, showing all formulas and diagrams used. If you use diagrams to solve it, show the diagrams. If you use the formulas to solve it, show the formulas. The number of people only in A. The number of people only in community B. The number of people only in community C. People in community A or B or C, or all of them. People exactly in one community. Most of the topic on set theory today was taken from the book of Seymour Lipscott's Discrete Mathematics. That's the ISBN, and that's the link on Amazon. Also, the Python codes on sets from the Python documentation on sets. The rest of the bibliography remains the same. Please like, share, comment, and subscribe for more videos. Thank you, and see you in the next class.